sphere at the center of C2 with radii of curvature R1 for sphere 1 and radii of curvature R2 for sphere 2. An intersection of these two spheres is this length. So the focal length is a number, is a distance from the center of the lens to the point that we can say theoretically all the rays that are parallel to the optical axis of the lens get focused into one point. The next topic that we need to understand is the optical axis of the lens. So when you have one sphere in space and another sphere in space, as I said, the cross section of these two spheres is a lens, and the center that connects the line that connects the center of C1, the center of first sphere, to the center of the second sphere, that line we call it the optical axis of the lens. And any ray that is parallel to the optical axis of the lens will focus into one point, and the distance of that point from the center of the lens we call it f, or focal length of the lens. So now let's see what is the equation for focal length when we have a lens that the radii of curvature of surface 1 is R1, radii of curvature of surface 2 is R2, and the thickness of the lens is D. So the equation is followed by this 1 over f, so we should be very careful. We are solving for 1 over f equal to n minus 1. N is the refractive index of the lens. It can be glass, it can be water, it can be any biological material like our eye, that for cornea we have a different refractive index which is close to water than glass. And 1 over R1 is the radii of curvature of this surface, 1 over R2 radii of curvature of this surface, n minus 1 times d is the distance from these two surfaces, over n times r1, r2. So we should be very careful. Here we have 1 over r1 minus 1 over r2. So we should put the actual value of r2 based on the lens convention that I explained. For example, here r1, the center point is in positive direction. So R1 by itself is a positive number. For example, the radii of curvature is 100 millimeter. So we put 100 millimeter here. Now for the second surface, R2, the center of that second surface is on the left hand side. Let's say we have the same R2. So R2 in this case is negative 100. So we have minus 1 over negative 100. So this negative cancels, and at the end we have a positive value as a whole here. So the same for the rest of the equation. Now for very thin lenses, when the D, the thickness of the lens, is much smaller than the radii of curvature of the lens. For example, usually R1, R2 are big. So when D is pretty thin, we can use this equation, which is another approximation, which is equal to n minus 1, 1 over r1 minus 1 over r2. And we usually use this equation, and this is a good approximation.